So here's the sort of mishmash of things that we're going to talk about. We're going to talk about debuginfod, which is pretty cool, and new user-defined commands and some of the new stuff about them. We'll some configurability of backtraces, which is good. We'll look at TUI mode and Python together, which is as I say, is awesome. There's a compile command, which I didn't know about until quite recently. It's not new, it's been around for quite a while, but it's a bit better in the later versions. It lets you compile code and inject it into the program you're debugging. And some details around conditional breakpoints, which I think are generally very useful, and they're getting a bit better. So let's talk about debuginfod. But before we get into that, we're going to sort of step back a little bit and kind of refresh or have a sort of 101 on how executables and debug information and all that kind of stuff works. So when I type GCC or whatever my favorite compiler is, I always say -G. I always say -G3 because that just gives you more, it's just better, I think. But -G or -G3 hello.c, well, what happens? Well, we generate, if we don't tell it what it's going to generate, the file's going to be called a.out. It's not really a.out format, of course, it's ELF. A.out is a legacy format. In fact, support for it has been removed in the very latest Linux kernels, so it's now officially a dead file format. We still call it a.out. And an ELF file consists of various sections, right? Now, there are a lot more sections than we've got here, but I've just given some of the more interesting ones. And I can view these sections with a utility called readelf. So here's my hello world.c. And if I go readelf -- sections on a.out, it lists all the sections. It's a slightly unhelpful layout, that one. So if I go capital W, it gives me the wide layout, so I can see a bit more what's going on. So a lot more sections than I said. We certainly won't go through all of them, but we've got. We can find here. If I look carefully, we'll find there's the text section. So the text section it's the code, right? It's the machine code that the compiler generates. It gets called text because, just to confuse everyone, I guess, I don't know why, but it gets called .text for some kind of historical reason. We can see we'll have .data somewhere. Well, there's .ro data. RO data is read-only data, so it's strings typically, but any constant constant things can get put there by the compiler, so that'll typically get mapped in memory without write permissions. So if you try and change it, it will likely segfault. And .data is going to be, there it is, look, and that's the initialized data, the initialized global data. If it's uninitialized, which means, of course, 0 initialized, it goes in this section called BSS, which is block started by symbol. They all start by, I don't know why, it's, again, historical reason, but that's still so I've got all these sections that make up my executable. When that program that lives in one file on the disk. When the program is run, some of these sections get mapped into memory, right? They get mapped in with mmap, with the file backing, so it all gets demand paged as needed, nice and efficient. So the text, obviously the code needs to live in memory, that'll get mapped. The data and the read-only data will get mapped. As I said, the read-only data will likely get mapped with read-only without write permissions. It depends on the operating system, of course. But the symbol table and the debug info will not get mapped into memory, right? They just sit there on disk when your program is running normally. But symbols and debug info often gets kind of conflated, and sometimes it gets called debug info, sometimes it's called debug symbols. But essentially, symbols are sort of the names of functions and things like that. So where main lives, what offset main lives at inside memory, that's in the symbol table. Debug info will contain the mapping to the source code, so different lines of how different program counters map into the lines of the source file, structure, layout, type information, all that kind of stuff. So we can see this. So if I compiled with -G3. So if I start my program in GDB, I can start, by the way, puts a temporary breakpoint on main and then runs it, so it just saves you a small amount of typing. And here I can see it's got the source code and everything. Let's put it in TUI mode, because as I said earlier, that's just better. So there we are, everything you'd kind of expect to see. Now, if I compile without -g, so if I type start, notice it knows, even though it doesn't have any debug info. So because I didn't do -g, so there's no debug info. If I go layout source, there is no source code. It doesn't know where the source code is, and doesn't know anything. It won't know about types or anything. But it does know where main is, right? When I typed start, it was able to put that temporary breakpoint on main that you can see here. So in this, because I don't have debug info, then TUI mode's not much use. But so I can disassemble the main. It knows where the main function is. It knows how big it is, but it doesn't know where the source code is, right? That lives in the debug info. If I strip a.out, then it doesn't even know where main is, right? If I try to put a break on main, it says it's not defined. It says, do you want to make it pending on future? Well, I know I'm not going to load a library that contains main, so whatever. So that's kind of a bit on the difference between the symbol table and the debug info. But yeah, the real point is the debug info and the symbol table just stays on the disk. So if you specify -g or -g3 or whatever, it doesn't change the code that's generated at all, right? That's -o, different levels of -o that will change the code that's generated. And it doesn't even load, it doesn't change your startup time or anything like that. That debug info will just stay on disk. All it does, as far as any kind of performance things are concerned, is it makes the resulting binaries bigger. Sometimes, though, quite a lot bigger. My little Hello World program, clearly nothing, not a lot of debug info there. I was working with a customer just a few weeks ago who had debug info of over 50 gigabytes. This is a lot of, obviously it's a lot of data to ship around. If it's kind of on-prem type software, it's a lot for people to download, or if you're really old-fashioned, it's a lot of CD-ROMs or even more floppy disks. But even if you're kind of in some more modern kind of cloud-native world and you've got your Docker containers and everything, you don't want to be, starting up or your Docker containers with those 50 gigabytes plus of debug info hanging around, even though it just stays on the disk until you need it. So it's, oh, sorry, I've got a bit out of sync. So when we run GDB, or whatever debugger, it's going to look at the text, the code, the data, and everything by looking directly in the process. But the debug info and the symbol table won't be there, so it will read those directly off the disk. And the source code also, of course. So, yeah, but carrying around that debug info, it can be very big. So often we want to separate it out. So there's different ways you can do that. I just showed you using the strip command. We can use obj-copy, or we can do this thing at the bottom here with gsplit dwarf. So if I show you what that looks like. Can we see that? Let me just put this, I'm going to just bear with me a moment while I slightly reconfigure this window to make it a bit more, if you put it at the top, it should be more readable. There we go. Right, so I've got my a.out, but I've got this .dwo, which contains the debug info. So that can be useful. And if you've got these split dwarf items, you can get for different, as you can see, it's for different source files, and GDB will demand load these in often. So with that example I told you about with the 50 plus gigabytes of debug info, GDB took, I think it was like an hour to start, just to slurp all that debug info in and figure it all out. But doing split like this with the split debug info, it will lazily load those as it needs it. So much more kind of usable. But can be then painful because, if I've shipped this binary and I've got my debug info, or deployed this binary and I've got my debug info somewhere else, well, can I find it? Do I know where to find it? And if I do, is it, like, it better be exactly the same version, right, as the binary that I'm trying to debug, otherwise everything's going to get very confusing. So how do I manage that? Well, that's where debuginfod comes in. So debuginfod is it's a daemon, it's a server that will just serve up debug info as you need it, and it's now as part of most distros. So whatever your favorite package manager is, you can probably just install it and then run it. So let's see what that looks like. I'm going to just bear with me while I just move this for maximum readability. So let's say, so let's just do it the simple way. And so that's, and I'm going to copy my a.out into, I'm going to squirrel it away in this debug info. I've just made a directory just to put it somewhere else, and then strip a.out. So now when I run GDB, oh yeah, no debugging symbols found. Can't even find the function main, as we've seen. All right, because I've put the so I've got, just to be clear, I've got my stripped one there and my unstripped one hiding away there. You see that's 3 or 4 times as big. So what I can do is run my debuginfo d minus f, which tells it where to look, and I'm just going to say all my debug information is in there, and that's going to run the debuginfo d. It traverses that directory, slurps all the files in, and so now, if I can go over to another, I can go export debuginfo d URLs equals localhost. That's it. Oh no, I think it's capital S. Okay, so it's just running on the local host, but obviously this could be running wherever, and it's port 8002 by default. So now when I run, look, it's found them. It's actually cached, it caches them here, it's cached them, but it's found from the debuginfo d server. And so if I start, then it's all, everything's working and everything's awesome. Now, then the nice thing is, I can be confident that this will be the right version, because in that, if I look at that readelf thing again, and I want to look at the notes section of a.out and grep -i build.id, I get this build ID, this unique ID that tells me for that binary, and that will be used by the debuginfo d server to guarantee that it's, so it can so debuginfo d might have lots of different versions, and so you obviously a bit of plumbing with your build system, and you can be confident that you're looking at the right, you're using the correct, the matching debug info, and you don't have to have it locally on your system. So that's pretty cool. It's kind of, if you're familiar with the Microsoft symbol server, it's kind of similar idea to that. That's been around for a lot longer, but yeah, probably I think a little bit simpler. It's quite configurable, but it's also very easy to use. The defaults are sensible. And there's at elfutils.org, you can point your debuginfo d URLs at this elfutils, and it's able to be, you can configure it as a kind of federated system. So that actually federates out to various distros. Seems to, as far as I can figure out, Ubuntu not yet, but Debian and CentOS and OpenSUSE and others. And I've shown you how it works with GDB, but it also works with various other clients like Valgrind and SystemTap and a whole bunch of others. So this is kind of just a little bit of plumbing to get it going, but once you've got it going, much more convenient and less error prone. Okay, any questions or comments or other things on debuginfo d? Yes? Yes, you can. Can you use debug info without debug info D? Yes, you can. That's fine. Just debug info. You have to have it somewhere, and you can point GDB at it. You can says sets. I can't remember. There's a way to tell GDB what directories to look in for the debug info, but it needs to be on the local machine where you're running, or on a file system mounted on the local machine where you're running it. But yeah, debug info. Debug info D is just another way to use the debug info. Anybody used debug info D? Yeah, no, it's pretty new. Oh yes, you have. Okay, awesome. And satisfied customer? Yeah, yeah, yeah. Okay, that's enough of that. So there's a bit of a smorgasbord of different things. So now we're going to talk about user-defined commands, which is something that's existed in GDB for ages, some small tweaks in the more recent versions, so I thought a good excuse to talk about user-defined commands. You can do user-defined commands in two ways. You can use the Python API to you sort of define your commands in Python, and that's kind of just, I mean, better in all sorts of ways, but it's more flexible. You've got much more control, but it's a bit painful, and I can never quite remember what to type if I'm adding user-defined commands through the Python integration. But I can always remember how to do it just in the good old-fashioned pre-Python GDB way because it's super simple. So I can just I've got this command define, just to define a new user-defined command, and I'm going to like imaginatively call my user-defined command hello, and it's going to echo, and that's it, right? And now I've got this new command, and so that can be useful. It's got kind of a macro style. You know, if you find yourself typing long commands all the time, this can be just a nice, convenient way, and you can put it in your GDB init and always have them available. So that's kind of useful. We can. Again, this is not new. You can document commands as well, like this. So say hello. So now when I go help hello, it's like a proper command. You almost, well, you can't really tell that it's not an inbuilt command. So that's good. Then the thing that's been added is a small thing, but I think is quite nice. Is you've got this this ability to define prefix. So I can go define, whoops, define prefix hello, and now I can go define command hello, and I can have different versions. So let's do a version in English. Hello. Have I got that right? So now I can go, yeah, hello in English, and I can go define hello French, and we can go echo bonjour. And the reason this is just a little bit more than merely kind of syntactic sugar is when I go hello, I can tab, and it tells me the various completions of that. So it just helps a little bit. The GDB interface is, as I said at the beginning, super powerful and hideously undiscoverable. Like you have to kind of just sit there and read the man page. And if you're adding in new commands, you know, very, very undiscoverable. The only kind of small bit of discoverability that's in the CLI is the ability to tab and see what you might be able to type. So, yeah, so user-defined commands, very useful little tool, and now just a little bit better since GDB version 9 or 10, I think, because we can have these prefixes. And I can document them in the same, you know, as you'd imagine. And the names of user-defined commands can now use a dot character. Hardly revolutionary, but okay, handy. And also, I think that appeared in GDB 9 is the with command. And this is useful generally, but it's particularly useful for user-defined commands because you might want, if your user-defined command gets little bit more complicated, you might want to change some settings. So for example, pagination, right? Pagination just really often gets in the way, especially with user-defined commands. So let's say I'm going to have my user-defined command. I'm going to, well, if I disassemble main, that's not big, but notice it's calling put string here. So if I disassemble put string, that's a bigger function, and it does the pagination thing, right? Which, okay, fine. But that can kind of get in the way, particularly with user-defined commands. So maybe I want my user-defined command. I'm going to define, so define disassemble put string, and I'm going to say pagination, set pagination off, and disassemble put s end. So now when I disassemble my put string, cool. Except now my user-defined command has a side effect. I've now just disabled pagination, right? Which I probably did not want to do. Well, I could just change my user-defined command to put pagination off, and that, so as in, let's do it like this. Redefine, yeah, I'm going to redefine that command, pagination, set pagination off, disassemble, put set pagination on, so clean up after myself, all good, except, of course, what if pagination was already off? Now I've just had the side effect of turning it on, which I probably didn't want. So, well, I could, so prior to the with command, you can deal with this, but it's kind of painful. So I could, I can go, I can print, I think it's like this. No, maybe it's like, damn, I've forgotten how to do that. Hang on, I do have, where are my cheat sheets? Did I put it in there? Okay, I can't remember how to do that. Never mind, but you get it. There is. I just thought we could do that. Oh, I know. Maybe like that. No, all right, but I can do it with Python. So the Python, so just in case you haven't, a lot of people said they haven't used the Python, so I can type Python and I can start going, type my Python in, okay? And so I could start to get the, I can print, so the Python integration has a module called GDB, and through the GDB module I can start to get really into the innards of GDB from my Python, which can be very convenient. And I think this will work. So I can start to build into my user-defined command. There we can see, so I can start to call back into GDB and start to pull out its configuration. So you can sort of start to imagine how, yeah, I could build my user-defined command to figure out what pagination was, turn pagination off, do the thing, and turn pagination back on again. Yeah, but painful. So much better to go, let's disassemble, put string, let's redefine that with pagination off, disassemble. Why didn't that work? Oh, I think I might need to go, sorry, define put string with pagination off. Disassemble, put like that. Well, that's embarrassing. I had that working before. So, with pagination off. Ah, yes. Thank you. Disassemble. There we go. Right, that's what I wanted to say. Thank you for rescuing me. We can So you can run, since forever, you've been able to run commands via the shell command at GDB. So we can go shell cat proc self maps. And now I can do that. Now I can pipe like I got the wrong. Okay, who can tell what I've done wrong here then? That is supposed to work. Oh, yeah, so it's piping, it's going to pipe the, I'm trying to pipe twice. So I can pipe the output of my GDB command. So the equivalent of proc map, looking at proc maps is I can go info proc mappings like that. So that's just an inbuilt GDB command, and I can pipe that into grep stack like that. So kind of handy. So yes, I can shell out to a piped command. That's what I was trying to tell you. And then another little tweak thing: set may call functions on off, which is quite useful. So one way you can get caught out in GDB. Sometimes I think it tries to be a little bit too clever. You probably know that you can call functions in the inferior in the program you're debugging. So I can go call structcomp foo like that. Okay, now it does what you'd expect. It's going to call structcomp inside the inferior. But it might do something you're not expecting, which is also to call malloc. So if I put a breakpoint on malloc, and now, oh, I think it's because I've got my debuginfod to go, but I think this one is, it's just, have I got, okay, yeah, so I've got my debuginfod set up, so it's got a bit confused about what's available in malloc. Anyway, don't worry about that. Right, so I put a breakpoint on malloc, and now when I go, oh, look, it's all gone wrong because it called malloc. Well, actually, it'll call malloc twice. Once to allocate the left-hand string and once to allocate the other string. So we'll call malloc, put those, initialize those strings, and then call the structcomp function. And this, I can tell you from bitter experience, if you're trying to debug your own malloc library, it can get very confusing. And we can just stop it doing that with set may call functions off, and then it won't just call functions in the background for you, which can be good for sanity. Yeah, that's not true. So this came from, I was copying down from the sort of news of what's new in the latest versions, and as I've just demonstrated, I'm running GDB 11 here, and well, call will, and hang on, will print structcomp foo. But no, so I don't. That is a claim that I dispute. Right, backtraces. So improvements to backtraces. So backtraces are extremely useful. Obviously, I think most what the hell? Who uses the backtrace command in GDB? I would expect pretty much every hand to go up. Yeah. So let's look at some a longer backtrace. So I'm just going to use a catch point. Catch point's pretty cool if you haven't come across them. So I can catch various things. You can catch the raising and the catching of exceptions. So catch. You can catch, and we can catch system calls. So catch just call write, So it's kind of a breakpoint, but it's a breakpoint on the right system call. Note it's different from, I can also say break right, but that's not the same. That is putting a breakpoint on the right library call, right? The libc write function, which usually the write system call will go through the libc write wrapper, but not necessarily. It doesn't have to. If I put a catch, with my catch point, it's going to actually stop on the right system call. So we will see this. Let's run. Well, hang on. Where am I in my program? We've got no source available. Okay, fine. Let's just restart it. Oh, sorry, I still got my malloc breakpoint set. Okay, so it's hit that breakpoint that I set, that libc write function. But what I really care about for this little demo is the write system call. So if I continue from there, now it hits the catch point, right, which is the actual system call. And I wanted to get to there because the backtrace is sort of somewhat long and has lots of these are useful. It's got these arguments in it, but if you're passing around more arguments and you've got maybe a little bit less screen real estate, it can get a bit annoying, particularly if you're passing structures and classes by value and by reference. So I can do things like set print frame arguments. Let's do presents, and then it just tells me that there are some. Doesn't try to figure out what they are, which can be useful. Or I can probably more useful set scalars. So it'll tell me scalar values, but it won't try and expand structures and things, which again can avoid a lot of the clutter. And similarly for the frames, we can give long, short location and addresses and various other sort of configurabilities. A bit more configuration over backtrace, which is good. Newer versions have, you may have noticed, have I think I've killed. Why isn't that working? It's kind of a little bit pretty. My string's in red. It's got syntax highlighting, and works better still here. So that's quite nice. Except maybe it's not. I mean, that's actually on this projector. That hello world is not very readable, is it? So maybe we want to turn that off. So set style enabled off. There we go. And so depending on what you're doing, that might be more readable. Actually, you can configure this, or you can configure this to your heart's content if you're that way inclined. So tab to see what's available, and you can see how I can configure all these things, including my TUI border and all the rest of it. Yeah, but usually set style enabled on. That's a little bit nicer. P-type is not a new command, but is another one that's new to me. When I was looking through what's changed in the latest versions of GDB, I found this P-type thing, and actually super useful. So and just got slightly more useful. So here's a ever so slightly more complicated program, but one that defines a structure. So here's my structure. And if I go p-type, whoops, what's the p-type struct foo, tells me the structure layout. Okay, that's kind of, well, useful-ish, right? But this is quite cool. Now it's telling me the offsets and the sizes of the members in the structure. That's quite handy. Now this is not new. This has been available for a while, although not, I think, very well known. But now just minor thing, but even more useful. I can put next there, and I can get my sizes and offsets of the members of the structures and class and whatever in hex. That's a nice nice little life hack if you're using, if you need such things. Some new convenience variables. So this is kind of what it says on the tin, right? So if I want to know which version of GDB I'm using, as I claimed, it is indeed 11. That's what I think I was trying. What I was trying to get before. GDB setting. I think. Is that what I was trying to do before? Yes, that's what I was trying to do before, isn't it? So I can look at if I want to know what pagination it's set to. Annoyingly, though, it returns that it's set to 1. So if I go set pagination, I mean, this should be a NOP, right? Because I'm going to set pagination to what it already is. But it gets annoyed because it's supposed to be on or off. But anyway, still quite useful. And shell exit code and exit signal, again, does what you might expect. So grep, stack, proc, self, maps, echo, shell. No, not echo, print. I always get that. Print, shell, exit code. And of course, if I do that, it'll tell me it failed with 2, which is, as we all know, eno ent. Remember I said about the customer I was working with who had the 50 plus gigabytes of debug info, and it took over an hour for GDB to start. Well, in the later versions, they've allowed it they've added multi-threading to that symbol loading, parsing step. So on a multi-core machine, it will just fire up however many cores there are and munge through all that debug info, proportionally more quickly. I think this is a bit of a work in progress, to be honest, because I can't find any real difference in it. And when I've run it, it seems to really still only be running single-threaded. So hopefully that's something that's going to get better over time. I think it might be good for certain C++ demangling or something, but it doesn't. Not a lot of it is multi-threaded, to be honest. Okay. Now I'm going to show some. So I asked at the beginning example of who's used Python. Not very many people. Who used TUI, text user interface? Again, not very many people. So now we're going to show the two together, which is going to interest absolutely nobody because the intersection is going to be the empty set. But I think it's quite cool, and actually, I think it's nice because it gives a nice example. It sort of demonstrates how you really, if you can think of it, you can probably do it with the Python integration that GDB now has. So I'm not going to try and type all of this live because I'll never get it right. So here's one I made earlier. So this is so a little bit of Python defines this myWindow class. And it has this render method on it, and that render method is going to get called when GDB tries to render that window. And then I need to have a factory method here, factory function, which will return an object, a Python object of the appropriate class. And I'm going to I've got some my crib sheet here because I'll never get this quite right. So we go gdb.register. Okay, so, whoops. So in the Python, it's gdb register. Oh no, hang on, I've got a source. So I'm going to source that Python we just looked at, and then I'm going to do some more Python, register window type, and that's where I put my factory function in. So that's my win. Is that right? think that's, did I get that right? Shell cat. So the class is, yeah, so we call the factory function, and I've called it mywin. I could have called it something different. That's probably a bit confusing. Doesn't have to match the class name, different case, obviously. And so that's now registered that window type. So now in the Python, it knows about that. And so now I can make a new TUI layout, which I will imaginatively call ACCU. So TUI layout, so I'm defining a new TUI layout called ACCU with the window type of mywin, and that's 10 lines of mywin, and then source is inbuilt, and that's going to have 20 lines of source, and then 10 lines of command. But I think I've got that wrong, because I think going to go like that. I have to give a command window, otherwise it doesn't like it. Undefined command TUI. What? TUI layout ACCU. TUI. Oh, new layout ACCU. But that's still wrong. There we go. Right. You have to give it a command window, because otherwise you kind of saw off the branch that you're sitting on, because you can't do anything else. But now I can switch to that. Oh, look, I called it ACCU, but anyway, I can switch to that, sorry, not TUI, layout. There we go. And look, it's made a new window at the top there, which imaginatively says hello world. So you can see how you can start to make this quite configurable. And in fact, you can go even further. I had a little bit of fun with this. You can actually see here, not just in, I've got a render function here. I can have a click and a v-scroll, so I can actually respond to the mouse click and the mouse scroll. And at the bottom of my source file, I've just put GDB.execute to avoid me having that problem trying to remember what to type. So if I go, GDB.a.out, start, so source TUI2. So now this, I can actually, if I do the scroll, I can actually scroll, and when I click, we should see it. There you are. It says it's clicked. So you can start to, you can see how you can build all kinds of fancy stuff. Are you ever going to want to do that? Well, probably not. But I just thought it was a nice example of how you, if you can imagine it, you can probably do it these days with the Python integration. All right, I mentioned the compile command earlier. So this is kind of cool. So, and yeah, I didn't actually know about it until quite recently. So let's step through. So I've got this function now, this structure x. So print x.a is uninitialized, so it just happens to be 12. Now, so I can compile. So I can set x.a equals, like, I don't know, like that. And sure enough, oh, interestingly, it's got a bit confused, doesn't it, where it is now? But it has, anyway, it's compiled that little bit of code and executed it. So that's quite a neat little thing. Compiled that, so it's compiled that code, injected that code into the inferior, probably did some malloc, I expect, knowing GDB, and then executed it. And there's been some fixes that make that a little bit more reliable in the later versions. Last thing I'm going to talk about today, we are racing through way much quicker than, usually talks take longer than you think they're going to. This one's going quicker. Anyway, that's all right, more time in the bar. Conditional breakpoints. So conditional breakpoints, well, we'll do another show of hands. Who has used conditional breakpoints? Okay, 50, maybe 30, 50%. I find I just use them more and more because they're just super useful. So conditional breakpoint, kind of what you would imagine. So I'm going to say break main. There's two ways to do it. I can go break main if, and then like argc is more than 4. I can't see why a main only ever gets called once, so I can't see why you'd ever do a conditional breakpoint. Oh, my main doesn't even have an argc, but you get the point, right? The other way you can do it is, so that is, so that's break. So I put a breakpoint on main called breakpoint 2, and I can go cond 2, and then I can do my condition, which that's a completely pointless condition. Of course, that breakpoint will now never trigger. All it'll do is make my program run more slowly. So conditional breakpoints are super useful. Don't need an amazing imagination to see how that could be really handy. Actually, there was oh no, I'll come back to that. So let's now take this little piece of C++ code which has a function foo which is overloaded, right? And so now with older versions of GDB, whoops. If I'm going to put a conditional breakpoint on that, what's going to happen? So let's. This is old GDB 9, and so I'm going to go. Well, if I put a breakpoint on foo, there's actually so it says 2 locations, right? I've got 2 foos. And info break. Okay, this all makes good sense, right? 1.1. Okay, I've got breakpoint 1 and actually breakpoint 1.1 and 1.2 for my 2 foos. But what happens if I now go? Well, let's delete that breakpoint. Let's go break foo if x is more than 2. But if I look at my that should, did I get that right? So x, yeah, like x is a parameter, it's an argument to foo, so that should work, right? Break foo if x is more than 2. Doesn't like it. The reason it doesn't like it is because it's tried to put that condition on each of the foo breakpoints. And one of them has a thing called x, but the other one doesn't. So it's kind of a bug, right, basically, and that's fixed in newer GDB. So now I can go break foo if x is more than 2, and it's set. It's done. It's put the condition where it could, and it's not where it couldn't. So now the one that the version of foo that has an x will have that condition. The one that doesn't have the condition, it's actually disabled the breakpoint, but at least it can. I can do what I need to do there. Last thing that I think I'm going to talk about is I noticed on some previous talks that I'd given, some people got quite upset on the YouTube comments that there was some reference to feeling sorry for Windows developers, and some people got quite upset that the debugging on Windows is like way better than using GDB. So I thought, well, okay, I'm up for a fight. So certainly Visual Studio and the like's much more discoverable, but I noticed in Visual Studio recently they added this awesome feature of, what do they call it? Dependent breakpoints. And so the issue is, I've got some function, like, I don't know, I want to put a breakpoint on structcopy, but only when this particular function is running, right? So I don't want to get all the struct copies. I only want to put a breakpoint on a struct copy from my function foo. So Visual Studio had this big, yay, we've got this thing called dependent breakpoints now, and you can right-click and go through all the layers of menu. And you thought, well, but GDB's been able to do that forever, right? Because I can put my breakpoint on foo, and then I can hang a command off that. so that when, let's not do that way. Let's do, well, let's do it like this. So I can put my breakpoint on main, and I can add commands to that, and I can then put the breakpoint on struct copy and continue and end. And so I've now got what Visual Studio was delighted about having these dependent breakpoints, being able to do that forever, because you can type at it, right? And generally in computing, when you can type at things, you get a lot more, it's a lot more expressive, and you can compose all kinds of advanced behavior. So, yes, that was way quicker than I was expecting, but that is my talk. Any questions or comments or anything to add? Yes?
On the user-defined, has things, some user-defined that has been created by someone that are useful, generally useful, that could be used by everyone, or do we need to create?
Yeah, okay, so the question that I think, so you're saying, is there a good place to go and find user-defined commands that are generally useful, like GitHub or somewhere, and find all these There must be all kinds of stuff out there. I don't personally know of any, so I guess there's some Googling to do there. What would be some good user-defined commands? There are certainly, I mean, there's things like GDB dashboard, which you may know about, which is user-defined commands and all kinds of stuff, which gives a nice view of GDB. And yeah, I mean, where I've used the user-defined commands is more in that they've been relevant to the project that I'm working on. I think that's where they kind of come into their own. But yeah, there must be all kinds of generally useful user-defined commands out there. Any other questions? Anybody know any resources of useful user-defined commands? No. Oh yeah. Yeah. Tips for working with projects with loads and loads of threads. Yeah, and you find it can get confusing just like knowing what thread's running. And do you know about set scheduler locking? Okay, so there's a thing, set scheduler locking. Off or on. So if you set scheduler locking on, then it will only work within the particular thread where you're stopped. So this can be quite useful if you don't want other threads to like hit breakpoints and things like that. If it's on, then everything's within that current thread. So if you can continue, none of the other threads will run. If you put it on, if it's on step mode, then when you're stepping, and I think next, only that thread will be stepped or nexted, and other threads will not be run. And when you do continue, all of the threads will run. So continue and step are different. The default actually changed, I believe, in roughly GDB 8 to step. So I think if we, oh, it's set to replay. Huh. What does that mean? So unlocks during normal. Okay, so this is, yeah, so replay. So GDB has this inbuilt thing, process record, where you can do time travel debugging or reversible debugging. And of course, you can use it with RR, and you can also use it with my company's stuff, which is completely awesome, and allowed you to just see like what the program had done. And there when you're using in that mode, you've got record mode and replay mode. Record mode, the program's running for real. Replay mode, you're seeing an execution of like what happened. And so that's what it means with there. It's got different different defaults based on where you are. But I think I think these days on modern GDBs, when you step, it will just step that. If I know, it will just step that thread, which is kind of useful. And you can mess about with scheduler locking. I don't know of any other tips around multi-threading other than time travel debugging is really useful for multi-threaded programs because of one of the horrible things with multi-threaded programs is that they typically do different things each time you run them. So if you need information about what happened in the past and then you rerun and it does a slightly different thing, and it's really hard to know what's going on. When you've got time travel debugging or replay debugging, that problem goes away. You just capture it once, and then you can explore that program history and state, knowing that exactly the same execution happened, same thread interleaving. All of the time travel debug implementations, however, do have a big downer with threads in that they will serialize those threads' execution at record time so that they can replay exactly the interleaving of the thread's operations. But they mostly will, it depends on the technology that you use, but most of them will still enable you to capture most race conditions. And if you can, that's good. I can imagine you could do all kinds of useful things with the Python integration to start saying, well, these threads I don't care about, they're kind of background worker threads, and I just want to kind of hide them. I'd imagine you could find a way to configure GDB to do that, although I've never done it myself. Yeah, question?
Reverse execution a lot.
Sorry, say again?
Have you used the reverse execution?
Yes, yeah, I have used it like a lot, all the time, because that's my job. Not the inbuilt reverse execution because it's just too slow to be useful, and that's harsh. It's so slow that because it does a single step, does a repeated single step and captures everything that happens. So if you have a particular function, a particular piece of code that's really kind of making your head explode, then you can enable recording just for that small section and it's kind of okay. It's also not really actively maintained. So if your CPU, if your program if the bit you're trying to record uses any instruction in relatively modern CPUs, it doesn't know what to do with it. However, you can use RR, record and replay, which is sort of separate to GDB, but much more useful. Anyone who's used RR in the audience? 1, 2, oh, not many. 3. Okay. So as we have a bit of time, let's. I mean, I don't know why I'm showing RR because it's kind of a competitor to my company, but. Let's see. I should have. Okay, yeah. So I think I've got a version here. So here is a program that does a bubble sort that contains a bug, which is intermittent, doesn't happen every time. I think, okay, so if I run it, it doesn't print anything out, just gets some random numbers and sorts them and exits. So that worked. If I run it again, that seemed to work. If I run it a whole bunch of times, like that, it segfaulted on the first one. Usually it segfaults after a little while. Okay, there we go. So it ran a whole bunch of times, and then we got a segfault and a core dump. So, well, let's have a look at the core dump. So what was that? That core was this one. It's GDB minus C core file. Okay, GDB terminated, program terminated with a segv. Well, I knew that. And what do you normally do when you load a core dump up? You do a backtrace, right? That's what usually one does. But this particular core file is no help at all. It looks like I've got some kind of smashed stack. So, of course, the core file just gives me a snapshot of the program state at the very end. And what I want to know is what happened. Hence, I normally do backtrace, because that's usually as close as you get with GDB to knowing what happened. But the backtrace isn't helping me, so therefore I've got no idea what happened. All I know is my program segfaulted. So let's try, I like this demo, this is kind of a fun demo. So I am going to, I can run it with with process record, which is the inbuilt recording thing. It's kind of slow, but it works. So start, I'm going to record. So this turns on recording. So now when I continue my program, okay, so that's what's happened here. So it says now the next instruction is a syscall exit group. This will make the program exit. Well, okay, so it's saying your program's about to exit. You might not want to exit. Yeah, no, let's stop. Do you want to stop the program? Yeah, let's stop here. So, well, this is obviously a good run of the program. It's run all the way to exit. It hasn't segfaulted. So I'm going to have to keep running it inside record until it crashes. And I could just stand here and repeatedly do that, but of course, we don't want to do that. So what I'm going to do is I'm going to put a breakpoint on main. I'm going to put a breakpoint on that function. I'm going to put a command on the main breakpoint to enable recording and to continue. I'm going to put commands on breakpoint 3 to run, just rerun. Okay, so when it gets to breakpoint 2 on main, it will enable recording. When it gets to the end, it hasn't crashed. It will just start again, which will hit the breakpoint at main and re-enable recording, and on we'll go. I will have to set confirm off, because otherwise when I do the run, it will say, you sure you want to run? So set confirm off, run. Okay, so this is going to keep running through that program. You can kind of see how slow it is, because it's a very, very small program, and it takes like a second to run with the recording. But eventually, let's leave that running in the watch pot never boils. So let's leave that going, and let's show how I could do a similar thing with RR. So RR record a.out. Okay. Right, so this is kind of the problem. So RR is pretty good, but the problem is it's kind of a little bit limited, a little bit fussy about where it will run. But that's okay, so we can do that. So let's T1, echo 1 into sudo T that. Let's see if that will work. Oh, okay, yeah, like I said, I haven't actually tried that on this. It's a new laptop, and on this particular laptop, this particular version of RR doesn't like the CPU. So this was not, this was not intentional. So live record, which is the thing that my company does, we can run like that, and it will run, and it will take a recording. I can also run it in UDB, which is our version. I'm going to have to give that, I haven't got a network, so I'm going to have to give that a local key file. And it's basically very like GDB, but gives me the ability to go next and reverse next. Okay, so my pot that I was no longer watching has boiled. So it stopped. A.out has stopped. It didn't get to the end, right? So this is a pointer that received a seg fee, and there once again is my nonsense stack. But I can go reverse step I. Remember, I've enabled recording, so this is going to go back exactly one instruction. And look at that. I'm in sensible land. So okay, it looks like I had a smashed stack at the end. So it looks like when it's issued that return instruction, or in fact returned out of the function, badness has happened. Let's have a look at the stack pointer. So when you return, well, actually, let's just look at the disassembly. So we are, it's going to be easy to do that. So we're here at the ret instruction. So when you return on x86, you will return to exactly what the stack pointer points to. So stack pointer points to that. So if I print, I could do x for examine, but I'll show you why I've not done that in a minute. Yeah, that looks not like a valid address. Let's just see. X for examine that address. No, cannot access memory. So my stack contains garbage. Okay, I kind of knew that because my core file was useless. But now I can start to examine, well, why is that? And I'm going to put a watch point on that stack address. Who uses watch points? Okay, yeah, half. Watch points are very handy. So you run the program until the data you're watching changes. But they're completely awesome with time travel debugging. So watch that. So I'm now watching the top of the stack, and I reverse continue, and that's like a continue, but it's going to run back in time until that watch point fires, which will be the point that that location of the stack was written to. So reverse continue, and yeah, that's not stopped where I thought it was going to stop. I can't remember. There is a reason it does that. I think that's a bug in process record. So, hang on a minute. What am I? Oh, yeah. All right, let's do it this way. So we're going to live record that program, doing the same thing. While live record that, do echo OK, done. So live recorder is like just like RR in what it does, but it's much less fussy about where it runs, and hopefully we'll get a recording that we can actually debug here. I still have the problem of this being a watched pot. There we go. Right, so this is my recording. So I'm going to do that I'm going to load that up in UDB. And now that's right at the beginning of the program, before main has even been called. So continue to the end. Now it's received this segv, right? So now if I reverse step I, okay, so this is looking a lot like before. So print top of the stack. Okay, print long star top of the stack. It looks like not a sensible address. Yeah. Okay. So now I'm going to watch. I want to watch the stack. No, hang on. Watch that. The reason I'm doing that, by the way, is that if you put a watch point with like $SP, it will actually try and watch what the stack pointer is changing to always. So when the stack pointer changes, it will change what it watches, and I don't want that. I want to watch that location. I want to watch that stack. Sorry? I think with -L it will probably work, but I daren't try, just in case. This will work. You can't beat typing hex. You know what's going to happen, don't you? Right, so now when I reverse continue, that's a bit better, isn't it? So it's hit the watch point. It's hit the watch point when it's writing into the array. So writing into the array has touched the stack, touched the top of the stack. Why is that? Well, I is 35 and type of array p-type array. It's 32 entries long. So here's the bug. Obviously, we are doing % size of array and the size of array in bytes, and then we're indexing it based on that. And if we're unlucky, it happens to be that top of the stack. So that was the longest possible answer to the question. But yes, I use time travel debugging all the time, and I don't know why anybody wouldn't.